And why? So why does that mean the curve is going to be lower? Because here I'm plotting against t, not against z. Right? I'm plotting against t. I'm plotting against t, not against z. Well, the reason why the true curve is going to be lower here is that for any given temperature, I will have had to have reacted more reactant to get there, because I lost some heat. So the F2 of C will be slightly lower. Yes?
You also get a shift in the position of the maximum?
I haven't spoken about the maximum yet. Wait till I get there. So, and this difference is smallest at the beginning because there's no heat loss at the beginning. So the true curve is going to be somewhat lower. And what happens to the maximum, I'm not really sure yet. All I know is it's going to be a little lower. So over here, there's going to be no difference because there was no heat loss. And eventually, but everywhere it's going to be lower because to get to a given temperature, I will, in reality, I'm going to need to react a little more reactant to get there because I'm losing heat. So therefore, the heat generation is going to be lower because I'm going to have a lower C at that temperature. But it's not huge difference. It's not a huge difference because the T dependence is more important than the C dependence. Now, whether the maximum moves to the left or to the right, I don't know. And right now, I'm not worried about that. Okay, so now let's go to the next case. Now remember, we're only going to be using this curve. This curve is only going to be relevant for Z less than Z max. I don't know where Z max is yet. And for T less than T max. I'm using this curve to try to determine T max when they're equal. Once I know where T max is, then I will figure out where Z max is. Okay, so I'm trying to use this note here. Okay, next, let's go to Z greater than Z max. When Z is greater than Z max, then I neglect this term. If I neglect this term, now I can just solve the heat transfer problem alone without the mass transfer problem because I have no rate anymore. So I have rho V Cp dP dV is equal to minus 2 over R, 2U over R, T minus T surroundings. Okay, I can always subtract a 0 here because the derivative of a constant is 0. And then I have dt minus t surroundings over t minus t surroundings is minus 2u over r rho v cp hat times dv. And this integrates to v, or if you like a dz, whatever, v. And this integrates to log t minus t surroundings. And here I'm integrating. I should be careful here. So let me integrate this dv. So here I'm going to integrate from t max minus t surroundings to some arbitrary z, t of z minus t surroundings. And here I'm going to integrate from z max, so this is just going to be a dz, to an arbitrary z. So this tells me that this is the log of t of z minus t surroundings divided by t max minus t surroundings. And that tells me that t of z minus t surroundings is equal to t max minus t surroundings, e to the minus 2u rho v cp at r times a z minus z max. That's if I integrate it. Now I've integrated it, that's very nice. I'm going to need that later on. But if you remember, what I'd like to plot here is the heat consumption. So this is the heat generation, and this is the heat transfer. Or heat transfer. And the pure heat transfer is just this term. So I'm just going to plot that term, the pink term. And this thing, and I'm going to plot it with, I'm looking to where these terms are equal, so I'm plotting it without the negative sign. 2u over r, t minus t surroundings. As a function of t, what shape is that curve? Goes up to you. It's linear, and it has a positive slope, 2u over r. So if I have some... I'm sorry?
There's a negative sign.
Yeah. Here, I'm looking when heat generation is equal to heat transfer. This is minus heat transfer. It's heat generation minus heat transfer. So I'm plotting the heat transfer. So if I have some sort of, I have some temperature T surroundings, and now when I plot this, I get a straight line. And the slope of this straight line is 2u over r. Okay, and where these curves cross is an estimate of T max. And notice the estimate is conservative because the true curve is below it, so the crossing will be to the left. So here we see that it's a conservative estimate of T max. Is that clear? Now, one thing you can notice, let's say my Tmax is too high. So what would I want to do? I want the curves to cross earlier, not later. How can I make the curves cross earlier? Volunteer?
Decrease the inerts in the system.
Decrease the inerts. What is decreasing the inerts going to do? That's going to make the system heat up faster and blow up the reactor. Yeah, well, that'll help us because that'll blow up the reactor earlier, so then we won't have to worry.
I use a material with the lower heat transfer coefficient.
Material with a lower heat transfer coefficient. You know, lower heat transfer coefficient will blow up the reactor earlier because it will keep the heat in. So if I increase U, use a material with a higher heat transfer coefficient, then I'll increase the slope. If I increase the slope, I'll move the curve. The pink curve will shift, and therefore they'll cross earlier. So one thing I can do is play with the heat transfer coefficient. Another thing is to change the radius of the reactor. Now, of course, it's a little dangerous. If I want to make the radius bigger, I may kill off the thin reactor assumption. So I have to be careful how I do that. But another way of doing it is just to, if I calculate that Tmax is too big, that could just mean I need external cooling. The simplest thing to do is just add a heat exchanger. Yes?
So why are you taking out the negative again?
This is heat generation minus heat depletion, heat consumption. So when the TdZ is 0, this term equals this term. That is, I set this equal to 0, and I move this to the other side of the equation, so I no longer have the minus sign. Okay, so let's see. All right, so, well, that's an estimate of Tmax. And now, but in order to design the reactor, I need to know the temperature as a function of, I need to know the temperature everywhere and C everywhere, because I need to eventually design my reactor. That is, I need to solve this equation. So I need to know T of C and how they both vary with, how T varies with V. So I either need to know T of Z or T of C or something like that. So again, what I'm going to do is I'm going to come up with an approximate profile. So this gives me Tmax. I'm going to come up with an approximate profile under these assumptions of the temperature as a function of z. And then once I know the temperature is a function of z, if I know T explicitly, then I can solve this equation. Okay, so let's solve the adiabatic equation. Z less than Z max, solve adiabatic. So let's solve the adiabatic equation. So the adiabatic equation, where is it? I've got dt dz, dt, I've got rho v cp hat, dt dz, dt dv, make dt dz, and I've got an area here, is equal to minus RA times minus delta H. Okay, now RA, we know is, so I've got minus delta H, that's a constant, I'm assuming that's a constant. And now I've got K, minus RA is K of T, times F2 of C, but C varies linearly with T. It's equal to rho Cp hat over minus delta H, T of Z minus T. So now I have an equation with a T here and a T here, and I've eliminated C, so I can integrate this equation. So if I integrate that equation and I plot T as a function of Z, I get an equation that looks like this. Why does it look like that? I know the temperature. Initially, when I have an adiabatic equation, we said initially the temperature goes up exponentially. So here it's going up exponentially. And then eventually the reaction slows down because I run out of reactant. So then it starts to level off. So the rate goes to 0. So it has to look like this. It starts out exponential, and eventually it slows down as the reactant peters out and flattens out. This is adiabatic. The temperature never goes down because there's no heat transfer. Okay, so let's make that curve blue. All right, but now we know, but we already have an estimate for T max. Where is it? Here. We know what T max is. So we go along here and we say, aha, T max is here. So we only keep this part, the part of the curve that goes to T max. Clear? Yes?
How did you get that again?
What is that?
Oh, the T-max.
T max over here. I look where the pink curve crossed the blue curve. That gave me, and then I just read down, that gives me T max. So now I have this curve, the adiabatic curve. The adiabatic curve is blue, but I only keep the blue curve for Z less than Z max. At Z max, I throw out the rest of that curve. Now we just integrated what happens, and then I move to the second one, Z greater than Z max. Now that I know what T max is, and I know what Z max is, because once I have T max, I can read down and I know what Z max is. Now I go to this solution, which was the integrated pure heat transfer equation, and I have an exponential decay. Exponential decay in Z minus Z max. T minus T surroundings is T max minus T surroundings times an exponential decay. So that says that this curve looks like this. And that is my approximate temperature profile. And I haven't needed any big computers to get it. Okay, so what happens here? I have my estimate now for T max and Z max, which is the most important thing. If this value is too high, I know I need cooling. If it's not, then I can design my reactor. If it is, I put the cooling in and then I design my reactor. So how do I design my reactor? This is clearly not what the true temperature profile looks like. It's a crude zeroth order approximation. So I'm going to call this T zeroth approximation, super zero. It's the zeroth approximation. And the question is, can I improve this approximation? When I do my design, I kind of want to improve it. So this gives me the temperature. And I think you can see how I might improve it. Because from this temperature profile, I can now come up with a crude concentration profile. I take this T0 and I stick it into the design, the mass balance. If I know T0 of T of Z, if I know T0 of Z, now the mass balance will, once I explicitly give you T0 of Z, that curve over there, now the mass balance equation is an equation that only involves C, is the only unknown. So I can integrate this equation to get the C of Z that corresponds to this T of Z. So I take this T of Z, T0 of Z, and I put it into the mass balance equation. And that, when I solve it, I get C0 of Z. I get the concentration profile that corresponds to this goofy temperature profile. Okay, well now I want to do better than that. So now I take this concentration profile and I go to this equation, the heat balance equation, where now C is explicit in terms of Z, C0. And now the only unknown is temperature, T, T, and T. And I can integrate that equation. Let me do that integration, and part of that integration explicitly. Because if I bring this to the other side of the equation, I have a first order linear differential equation that has an integrating factor. So I have d dt, d dz. Well, I've got rho v cp hat, rho v cp hat over a dt minus t surrounding dz plus 2u over r t minus t surrounding is equal to minus RA, or minus delta H, minus RA of C, but now C is known, C0 of Z, T. And this is a first order linear differential equation. So let me multiply by, get rid of these constants. So I have an A over rho V Cp hat. A over rho V Cp hat. I get rid of this. And now I get it, I have an integrating factor. So the left-hand side is d dz of e to the A to U over rho V Cp hat R times Z times T minus T surroundings is equal to e to the 2AU rho V Cp hat R Z times minus delta H times minus RA from C0 of Z T, which I can integrate. And if I integrate, I get T of Z minus T surroundings. And if T in is equal to T surroundings, this thing times, if T in is equal to T surroundings, the bottom limit is just going to give me 0. And this is equal to e to the minus 2a u over rho v cp hat r z times, minus that, times the integral from 0 to z of e to the plus 2a u z prime over rho v cp hat r. All this is a constant, so I'm just carrying around this constant for nothing. Times minus delta h, another constant, times minus RA of C0 of Z, dZ prime. Okay, so what have I done? I've taken this C0 of Z and I've plugged it into the the enthalpy balance, but what's simplified in the enthalpy balance is now C0 is no longer unknown. Since C0 is now known, this equation is only an equation for T. T is the only unknown. So I can solve it, and here I wrote it as quadrature. So I've got just T of Z minus T surroundings is this thing, where I use the integrating factor to combine these two terms. When I solve this equation, this is going to give me a better approximation for T. So when I solve this, put this into the heat balance, H balance. When I solve, I get a better T1 of Z. This will give me a solution that's better than this. This will give me a T1 of Z. Once I have T1 of Z, I can go back and plug it into the mass balance and get a C1 of Z. And then I take my C1 of Z, I plug it into the enthalpy balance, I get a T2 of Z. And I can improve this. And this is the basis for, if you write a numerical code to solve these two equations simultaneously, this converges incredibly quickly. Just in a few iterations, it's completely converged. And what you see here is not only does thinking about the problem physically give you what you need in the answer before you do any calculations, but even if you want to do the calculations, it tells you how to do the calculations in a way that converges extremely rapidly. Are there any questions on that?
Just one general question. So I know for the zeroth, it's like extremely crude, but it's a discontinuous function because you go from...
It's a discontinuous derivative. It's not a discontinuous function. The function is continuous. The derivative is discontinuous.
Yeah.
Because we have the derivative here. But do you have a problem with discontinuous derivatives?
Well, I just thought that it might be hard to, I mean, so if, say you were writing a program to solve this, if it was a discontinuous function.
We are writing a program. I just told you how to write a program.
Yeah, if it was a discontinuous function, that might...
Even if it were, first of all, it's only the derivative that's discontinuous and not the function. And second of all, the way we've structured this, we're only doing integrals numerically. We're never taking derivatives. So I never have to take the derivative of something that's discontinuous. I'm taking integrals. Integrals smooth. Even a discontinuous function I can take integrals of. At both stages, I'm either integrating this equation or I'm integrating this equation. It's a straightforward integral. I can write the top one as a quadrature as well. I just take, if I write the top one, I can also write it as a quadrature. Here it is, just the way I did it here, because now RA, well, I just have to be a little more careful. If I write this one as a quadrature, which I didn't bother doing, I have V, D, C, dV is equal to RA of C, and now T is explicit. T 0 of Z. Well, this is equal to A of T0 of Z times F2 of C. I can separate this. I have a quadrature. So this is equal to, I'm going to write this as ABZ. So I have DC, I have a V over A here, over F2 of C is equal to K of T0 of Z dz. And I've got all the z's on one side, all the t's on the other. So again, I can write this as a quadrature. This is an explicit function. This is an exponential. I can integrate this from 0 to z. And I can integrate this from C in to C of z. So all I'm ever doing are integrals. Here's an explicit integral, and here's an explicit integral. So it smooths everything. Other questions? You have a question? Did you have your hand up a minute? Okay, any other questions? All right, well, we still have 5 minutes to go. All right, let's see if that clock is right. Yeah, we still have 5. So now I'm going to just try, we just have a little bit more to finish up on non-isothermal reactors, and then we'll be ready for another test. Exciting. Means I should probably give you back some of the other tests. Question is, how does temperature affect selectivity? So I'm going to erase some of this. You have a question?
No, I just want you to erase this because
All right, so I'll write over here. I don't have that much to write because we only have 5 minutes. Okay, so we can take your pictures later. So how does temperature affect selectivity? Well, let's say I have 2 reactions. A goes to R, and A goes to S. Reaction 1 and reaction 2. So if R is the desired reaction, then certain things are pretty easy. If I want to look at little phi R over S, remember little phi? No. All like 2 weeks ago? Pre-hurricane, pre-Sandy. What do I get here? What is this? Give it back to the woman in the green. What's the little phi here? You look at your notes before today? Yeah, it's RR over RS. Okay. So what is RR and RS? I can't hear you. Right behind.
Oh, it's negative K1 CA.
Plus K1 CA. Divided by
K2 CA.
K2 CA. Yeah. So here I'm just allowing them both to be first order reactions. The CA's cancel, and I have K10 e to the minus E1 over RT over K20 e to the minus E2 over RT. So notice that this is just K10 over K20 e to the minus E1 minus E2 over RT. So notice if E1 is bigger than E2, then a higher temperature raises this. If E1 is less than E2, a higher temperature lowers it. So what we see is that the higher temperature favors the reaction of higher activation energy. When I say favors, I mean it accelerates that reaction more than the other one. And that's also true if I have A goes to R goes to S. So if reaction 1 has a higher activation energy than reaction 2, if I want R, then I want to make this reaction faster than this reaction. So raising the temperature is a good thing. So I want a high temperature if this E1 is bigger than E2. On the other hand, if E1 is less than E2, E1 is less than E2, then if I raise the temperature, I'll accelerate the production of S more than I'll accelerate the production of R. So I want low temperature. What's the problem with low temperature? Slow reaction. So if I'm worried about, so it's slow reaction, that means I need a very big tau. Well, and that brings up the point, which is the final point I'm going to make today, before I give you another example, before I give you a question. The final point is the optimum temperature depends on the question. And the question could be, do I want to maximize the amount of R, or do I want to maximize the selectivity of R? So there are two questions. Do I want to maximize phi, the selectivity, or do I want to maximize FR out minus FR in, which is phi R over A, FA in minus FA out. Which one do I want? Well, that depends. If my separation is cheap, then I just want to efficiently make R, and then I'll just take the A out and recycle it. If separation is expensive, I don't want to separate, so I just want to maximize the amount of R I get out. Notice I'm maximizing different things. Here I'm maximizing phi, here I'm maximizing phi times delta FA. Sometimes making this big will make this small. So for example, in the case we just did, we just said where reaction 2 has a higher activation energy than reaction 1, then high temperature is bad because it's going to make this reaction go fast. Low temperature is good in terms of phi. Low temperature will slow this reaction down a lot more than it slows this reaction down. So it's going to make phi better, but it's going to make FA in minus FA out worse. So you can imagine there'll be some compromise. Too high a temperature, I get all S. Too low a temperature, I get R, but I don't get much of anything. So there's going to be some compromise temperature. So we're going to have to, so we expect a compromise. If this is the question, we're going to get compromise T's. Another case where we'll get a compromise T is if I have A goes to R, S, T, 1, 2, 3, where E1 is bigger than E2, but less than E3. So I want a high temperature for 1 relative to 2, but I want a low temperature for 1 relative to 3. So this will also give me compromise temperature. And the compromise will be the we'll call optimal temperature, and that's what we'll start the next hour with. So we'll do about, it'll take us about 10, 15 minutes to get through temperatures, and then we'll move on to the next topic. I neglected to put the homeworks in my box, so I will do that today. The homework on non-isothermal. Are there any questions? Okay. Unfortunately, I know this is going to be a big disappointment. We've been meeting every day, but tomorrow we're not going to meet. So you're going to have to survive